coupon collectors. Just like a show of hands, how many people finished that and adjust the run on the largest size like under like 10 minutes?
Which one?
The largest size on the coupon collectors. How many finished that under 10 minutes? All right, so how many finished under, and just the runtime, under 30 minutes? Okay, great. And how many finished under like 1 minute? Few people under a minute. Okay, cool. So there's a wide array of that, and kind of the like it's fine. You aren't gonna lose any points if the runtime was longer. It was partially, I wanted to make sure that the runtime made sense to verify that you actually did what you're supposed to for the assignment. But also, it's kind of worth noting that there are differences in how you could have programmed it, and if something takes a long time, it's not necessarily because it has to be that slow, but there might be ways to make the same task to just do it faster. So of those who finished, who had the runtime, who the runtime was like under a minute, do you want to add anything about how you did, what language you used?
I did it in C.
So in C. Okay. Yeah. So like what, do you use a data structure to keep track of?
Yeah, I used a character array just to contain really a 1 or 0 Boolean value. And then I used the random number to index into that, change it to 1 if it appeared. And I just kept a count of the amount of numbers I found, so I never had to go iterate through the array ever. So.
Oh, cool. Great. So does everyone understand that? Everyone hear that? Should I repeat it?
Yeah.
So, so all you need to do is store a like single array. Start with the array, so it's all like so you can start with the array up to size m. Start with the array like it just has to be binary. It can be characters and integers. That's fine. Start with everything as just like zeros everywhere, and then if you generate random numbers. If you find a 0, change it to a 1, and have a counter that increments how many times you change something to a 1. If you see a 1 again, you don't do anything, but if you see a 0, you do that. And if the counter hits m, then you've hit everything, right? So you didn't actually have to keep track of any of the counts or actually what any of this stuff meant. You just needed a counter on the side, right? And then if you do that in C, you can do it even faster. There was something posted for if you're using Python. There's a library called Numba that allows Python to precompile things, and then if you have like for loops and stuff, it'll unroll the for loops so that it runs a little bit faster. C might do some of the stuff. Kind of, it's trying to compile. It has a compiler, so it's trying to do the stuff automatically. But Python may not automatically try and do some of these tricks. Okay. So the first homework was turned in. If you have not finished it, you can turn it in late. It's only 10% off within the first 24 hours and 20% off the first 48 hours. If you turn it late, you should still do it. I still want you to learn all that stuff. The second homework, so the homework for the document hash link right there has been posted. I updated the assignment on Canvas, and I think I had it so it sent out an update that notified you it had been updated. Is that correct? No? Okay. Well, it's it's now been posted. You can either find the thing linked on Canvas, or you can go and click on here. Okay. And if you see the assignment, there are 4. So there are now 4 data sets which are online. You can download. Each of them is just a string of just like a string of characters. and you're going to do you're going to create the k-grams for these strings of characters. And I'll ask you to do it in 3 different ways with either with the characters or like using the words. And I've removed a lot of the modeling questions. I've taken out, or the TA took out punctuation and made everything lowercase. You can see it's lost a little bit of the meaning and the context if you actually look at the documents, but you can still see what's going on. And so I'll ask you to create those. So I'll ask you to kind of create all these different combinations, and we'll post a couple numbers on Canvas so you can do like so you can just check to make sure you're not off by 1 in these numbers. But you'll fill in the rest of these tables, and then you'll compute the Jacquard. And you'll compute the Jacquard similarity using these different representations. Okay. And then what we're gonna talk about today is a different representation. Instead of internally storing them as like sets, we're going to kind of do something called min hashing on these sets, which will ultimately be a simpler way to simpler representation. For the size of these documents and only having 4 of them, it's not really that meaningful. This is meaningful at the scale of all the web pages on like Wikipedia, right? So if I have every page on Wikipedia, I want to keep track of measuring stuff in between those. At that scale, it makes sense. With 4 things, well, you know, you're getting an example to do it so you see how it works. But it's not going to give you a lot of computational advantages at like this size. But it's still experience. Yeah. So okay. So that's due in. That's going to be due in like 2 weeks. The thing which is due in only the thing due in just 1 week is going to be the project proposal. Because next Monday is a holiday, there's no class next Monday, so this is the last class before the proposal. This should be a fairly short thing. I'm asking you to turn in. The main kind of task you're supposed to do is to form your team and come up with a rough idea of the topic. Okay, if we look at the document, so the proposal is supposed to be like on the order of 100 to 200 words. If it's a little bit longer, that's fine. But the point is, it's supposed to be short. I want you to start thinking about the idea. If you want to change it later, so that's okay. But most of you will stick with the kind of the topic that you're starting with here. And because you don't know the techniques in the class, you're not going to know exactly what to do. That's fine. But and so one thing is there needs to be one project proposal per team. But at this stage, I want all of you to turn it in through Canvas. Every team member should turn it in. After this assignment, we'll form the teams, and then you'll turn stuff in as a team. Only one person needs to turn in. But at this stage, just as a way that I can verify you're all on the same page, I want everyone from the team to turn in the same assignment. Okay. And so the first few steps of the project are basically going to be, if you follow the instructions, you're going to get full points. Okay, there's not going to be, well, this person's description was better than this person, so they get 3 and this person gets 5 points. Just if you follow the instructions, you're going to get full points. It's just kind of a forcing function, so you're starting to work on this. Okay, so who is in your group? What data do you plan on using, and where do you get it from? This could be a specific answer, or it could be kind of So something more vague at this point, that's fine. The next step will be the data collection report. Will you need something more specific? What structure do you plan for mine from the data? Again, you don't know everything in this class, so again, this can be fairly vague, but I want to get some rough idea. Why is the pump why is this interesting, and what would be new? What would the instructor learn from this? So it's possible it's on some project. I've seen kind of a similar project in the past. That's like okay, but I want it to be more than just, well, I ran the standard technique on this standard data set that 20 other people have run and posted their answers on this before, right? That's kind of uninteresting, but I want to try 2 types of clustering or 3 or 4 types of clusterings on this.
Is the purpose so we have it all in, like, each team member has it in our own words, or?
Oh, no, I want you all to write, I want one project proposal written, but then you all turn in the same one. It's kind of, otherwise you say, well, I'm on the team with this person, but they have a different idea. It just forces you to all be on the same page. I don't know. It's probably not needed. We'll form groups after this one, but this just ensures that we have the groups are kind of, the groups make sense. Okay. Yeah, so there are these 5 things I ask you to answer in 100 to 200 words. It's not a lot of words. I don't need a lot of detail, but I want you to kind of start thinking about this. And you can, if you want to change it later, that's fine, but I want you to get started. Okay, and so if a bunch of people have posted ideas on, so like on Canvas, of people who don't have partners, who are looking for teams. So now I know there are other people out there, so don't come to me and say you couldn't find one unless you replied to all those people and they all said they're all full. And the other way is just talk to people kind of next to you in the class. That's also, if people want to come up in front, and if you haven't found partners yet, you can come up in front after class. That's another great way to find partners if you haven't found them yet. And finally, I brought the posters in, I think for the last time for a while, of example projects from in the past years, which were at least reasonable. Okay, so any general questions on the project? Yeah.
You mentioned before, if we make this proposal, then we can go down this path and decide it's not working. We can switch this later.
Yes. Right? Yeah. So what I'll ask you to do is to go back and turn in the project proposal, return in the data collection report if you've gone that far and so forth, and just let me know. You won't be marked late or anything like that. It's just that way I've got a record of where you were at each step, and you can build on those steps. But this happens to a few groups every semester, and it's no big deal.
So what's the minimum size of the data you're looking for?
So it depends a lot on the project, right? So some data sets, having roughly 50 data points has worked, but it was kind of, each data point had a lot of interesting stuff to it, and so there was messy stuff. Other groups that worked with, they've gotten like the 1% feed from Twitter for they had that 1% of Twitter for at least a few weeks, which is a huge amount of data. They could not store it locally, right? So they had to go and rent some Amazon EC2 instances and so forth. People have done this in the past because they wanted to experience those sorts of challenges. And it really depends on what you're trying to do with it. If you come and say, I want to run this really complex analysis and I have 50 data points, where you really need a few thousand data points for that to work, I will try and give you that feedback, right, if your data set isn't a good size. Or if the data set is so big and you want to run an algorithm that's like an n squared time algorithm, I'm like, that algorithm is not going to finish running by the time the project is due. So you might want to kind of maybe trim down your data set, right? I've had to go both ways. Yeah. So okay. So great. And if you have any questions about this, after class, office hour is a great time to come and ask me about that. Okay. So we're going to be talking about min hashing. All right. So this lecture is I'm going to talk about a technique which I think can be a little bit confusing the first time you see it. So we're not going to go cover too much in this lecture, but I'm going to explain the technique, go through some examples, explain like why it works. But the full context of why it's useful may not materialize until the next lecture. Okay? But we're going to start again with the Jacquard similarity between two sets, A and B, which if we remember is A intersection B over A union B, right? So if we have that A equals 0, 1, 2, 3, 6, and B equals 1, 2, 4, 6, 8, then in this example, we're going to have the intersection is 1, 2, 6, and the union 0, 1, 2, 3, 4, 6, 8, and this is going to be 3 over, so like 3/7. Okay, so that's the Jacquard similarity. So like in between these sets, and our goal is going to be to figure out how to compute this, how to figure out how to compute this quickly, and not just for two sets, but for lots of sets. Okay, so the problem to think about is our data is going to be a set of sets. So say A1, A2, up to AN, and think of N is going to be something like 1 million. Okay, so think of that we have like all the pages on like Wikipedia, and this is a data set you can download and work with if you want to. And so we've run some form of our k-grams on this and translated each page into a set, A1 up through AN. And now we want to maybe do something that requires seems to require computing the Jacquard similarity between all of the sets. Okay? 1 million squared is going to be a lot, right? And these might be fairly big sets. There might be tens of thousands of words on many of these articles, right? So we want to be able to quickly determine which of the sets are similar. And what really matters is not so much if there's like what it means to be similar, but we want to find the ones which are very similar to each other. Which web pages are probably are maybe close to duplications of each other, or are in the same class somehow. If they're both talking about talking about basketball, there's going to be certain words which are going to appear more frequently than in some other categories. So we want to somehow figure ones which are in the same class or close to duplicates, and so we want to know if the Jacquard similarity is high between two sets. And so most pairs are going to be large, and we want to care if it's very high, and so we may not even need to compute this exactly. We'd be happy with some form of kind of approximation of this, as long as the high similarity ones stayed high and the small similarity ones stayed small. Okay, and we'll talk more about these trade-offs and where it means in the lecture on the lecture next week, and your homework will kind of start to see some of these differences in the examples you see. Okay. All right. So the goal is to kind of get a different. So what we're going to do is for each of these documents, what we're going to do is go from document, so there's a document DI, we're going to do a kgram, that's going to be into a set AI, right? So this is now a set, this is AI, this is a DI. What we're going to do next is we're going to do this trick, so-called min hashing, and this is going to be into a vector. So VI. We're going to do this for each of the web pages on Wikipedia. For each document, we turn to a set. We're going to turn it into a vector. Turns out, once we see this, you'll be able to observe that you can kind of basically skip this middle step, or it's implicit in the computation of this vector. Okay, and the vector is going to be a vector in Rk, so it's going to be of length k. K, and it's going to have so the property that as k gets so as k gets larger, then the Jacquard similarity between AI and AJ is going to be approximately by some approximate Jacquard similarity between VI and VJ. This is going to get closer. So I'm going to get a better approximation between the sets, which will be exact on the sets, but the sets had some modeling error in them anyways, and I'm going to get close to that on the vectors. It's not going to be exactly the same, but as we'll see, we can get arbitrarily close. As we make k larger, the vector larger, we're going to get closer and closer. And this will also it'll be easier to work with the vectors, as we'll see, in this context where we have many of these sets and we want to ask these, find all similar things, or here's a query of one article, I want to find all the articles which are similar to this article. I want to do those sort of tasks quickly, and this representation will be easier with the lecture that we'll talk about next week, with locality-sensitive hashing. Okay, so that's the main idea. We're going to go to this vector. Okay. So we're going to kind of have some intermediate step. Before we get to the vector, we're going to get a different matrix, say, / vector set representation. Okay, so I'm first going to get an exact representation. This one is going to be exact. So the one we're ultimately going to get to where as the length gets larger, it's going to be more accurate. We're going to get there, but we're going to start with a way of thinking about this, which is exact, but it's not very space efficient. Okay, so I'm going to turn each set. I'm going to represent set AI as a so bit vector. Call this BI, and this will be in 0, 1 to n. Okay, so if there are n possible things in the universe that my sets are out of, it's going to be a bit vector of size n. Okay, so let's go into an example here. Okay, so if I have S1, so let's S in there. Okay, so if I go with A1 is going to be 1, 2, and 5. And let's say in this case, we'll say n is equal to 6. So it goes from 1 up to 6. Then my bit vector representation of B1, I'm gonna write this as a column vector. The bit vector representation, B1, 2, 3, 4, 5, 6 of B1 is going to be, it contains element 1, contains 2, does not contain 3, does not contain 4, contains 5, does not contain 6. Okay, so now my set can be represented as this bit vector. There's a 1 if the element is contained. There's a 0 if it's not contained. Okay, and it'll be useful to kind of have a set of these sets as a running example, because we're going to change this representation, and it's important that that representation is changed consistently across all of the objects. So let me have a running example that has a few of the initial sets included in it. And this will be set 4 is 1 and 4 and 6. Okay? And so now the bit representations of A2 is going to be 0, 0, 1, 0, 0, 0. B3 is going to be 0, 1, 1, 1, 0, 1. And B4 is going to be 1, 0, 0, 1, 0, 1. Right? Okay. So I've taken these set objects, and it doesn't matter that these are numbers. I've just indexed them somehow, but I implicitly need to know what the full size of this domain is, which might be a little bit tricky with text. There are lots and lots of combinations here. We'll see how to get around this issue towards the end of this lecture. Okay, and then I'm going to have, so I just have these indexes, then I keep track of this vector here of bits. Okay, okay, so I have not lost any information here. I've not lost any information in this representation, and in this way of writing it, it's not so bad. But in the case where I'm modeling text, this can be extremely wasteful to write down all these zeros. For instance, in B2 here, there's a single 1 and there's a whole bunch of zeros, but if I think of all of the k-grams, there's going to be a potentially huge number of k-grams. Or if I think of IP addresses, I don't want to have a bit in my bit vector for every IP address, right? This is a huge vector, so storing all the zeros is not going to be a good way of doing this. Okay? There are sparse representations for bit vectors. Okay? There are a couple of simple ways of doing this. One is I just store the location of each one of the 1 bits. Okay? And it takes, there are n things in the set, it takes log n bits to store the location of each of the 1 bits. Right? So I save exponentially the amount of space if I have a constant number of 1 bits. And even kind of more clever trick, which is used in some cases, is I store them in order and I store the gap in between them. Right? So here I store, there's nothing here, then the gap is 1 to the first one, the gap is 0, 0, 0, 1. And so I just have to store the difference, but if I have these really big gaps, then this actually saves some in the space. Okay. We aren't necessarily going to need these bit representations, but this will be a convenient way of thinking of what's going on. So far, I've not lost everything here, but I've transformed my set of sets into this matrix. I can think of this matrix now. Here, a set of vectors is it's just a matrix, and if I have m columns or k columns, I have m or I have k different sets, and each row, n rows, then I have that many different possible elements in each of the sets. Okay, so I've got this alternative representation. This one is going to be more natural for most of this class and for dealing with and for thinking about. Okay. All right. So far this is all clear, right? It's all clear. I've just rewritten, stored it in a different way. Okay. But this is not that much easy to do a comparison. If I want to do a comparison, I can actually kind of scan down these 2 items in parallel and count them. You know, if I'm doing the Jacquard distance between B2 and B3, I don't count, if they're both zeros, I can skip that row. If one of them has a 1 but not the other, or if either of them have a 1, that increments the denominator. And if they both have a 1, that increments the numerator. Right? So I get the denominator between B3 and B2 is going to be 4, and the numerator is 1, so it's 1/4. So I can compute it here, but I've not gained any advantage on this large scale question yet. Okay, so this representation hasn't helped me so very much so far. Okay, so what we're going to do next is a trick called min hashing. Okay, and this is going to kind of take this wasteful vector, kind of bit vector representation, and so in the first, the naive, not the right way to implement it, but one way to think about it and analyze it, I'm going to take this representation and I'm going to make like k copies of it. Okay, each copy is going to lead to one element of this vector I talked about at the beginning. Okay, so it'll be, you can think about the space if you want to, but don't worry about the space. We'll use hashing as a trick to kind of reduce the amount of space. Okay, and this is going to have 3 steps. So I'll write down the steps and then we kind of walk through the example. So I'm going to randomly reorder. So I'm going to randomly reorder the rows, okay, of that representation. So the meaning of the bits, it doesn't matter if I have index 1 first or index 3 first. It's just an ordering. I'm going to reorder these. Okay, so for each set, and which is a column in this representation, I'm going to find the top 1 bit. Find the top or the first, so 1 bit. All right, so M of AI is going to be the top 1 bit. Okay, and so if we look at this example without the reordering, the top 1 bit for B1 is 1, the top 1 bit for B2 is 3, the top 1 bit for B3 is 2, and the top 1 bit for B4 is 1 in this ordering. But we're going to randomize this order. Okay, I'll go through a more detailed example soon, and then 3 we're going to repeat step 1 and 2. So k times. So I'm going to get a vector. Let's call this vi is going to be a vector of m1 of ai, m2 of ai, up to mk of ai. Okay, and each element of this vector is going to be the combination of step 1 and 2. So reorder and top 1 bit. Okay. Okay, so each row is the steps 1 and 2, and we get k rows for each of the vectors. Okay, so it's going to be these three steps, and I'll go through an example. But this is going to give us, and each one is done independently of each other. Each one is giving us a coordinate of this vector, and this will be our new representation. All right, so let's go through an example here, and we'll start with the same example, but instead of going from 1, 2, 3, 4, 5, 6, this was the original ordering of the bits. I'm going to do some sort of random permutation here, and this will be perm j, so the jth, corresponding to the jth row here, and I'll reorder these as 2, 5, 6, 1, 4, 3, right? So there's some permutation. Right, so each element is mapped to 1 in this new permutation, and then if I write down these bit vectors for B1, B2, B3, and B4, then I'm going to get, if I'm doing this correctly, let's see, 1, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0. Okay, so this is the same example so from before, but I've reordered the rows. So the first row, let's see, the first row was 2, right? So row 2 here was 1, 0, 1, 0, and if I check in the new representation, 1, 0, 1, 0. Right, so I did all the rows in the same reordering across all of the bit vectors. It's a known transformation that's fixed. Okay, and I get this new representation here, and then I'm going to right. Once I have this representation, I'm going to take the top 1 bit in each of the columns. Okay. Okay, so I'm going to say that mj of each of the items. For B1, this is going to give me 2. For B2, it's going to give me 3. For B3, it's going to give me 2. And for B4, it's going to give me 6. Okay? So these are all... So if I get this, that's probably not the right. Let me write this as mj of bi. This is going to be this, right? So mj of b1 is going to be 2, mj of b2 is going to be 3, mj of b3 is going to be 2, and so forth. Okay, so I've gotten so for one of the items, so for set AI, right, I've gotten, so for set A1, if this is the first column, the first row of this element, it gets a 2 here, right, which is going to match the value for B3. Okay? And so, all right, so the key property here is that so I'm going to get an estimate of the Jacquard similarity, which is between, say, I and j, which is going to be 1 if, it's going to be 1 if m, let's say I and I prime. Okay, it's going to be 1 if m of I equals m of I prime. Okay, and it's going to be 0. So otherwise. Okay, so if I just look at one permutation and one value, I'm going to estimate the Jacquard similarity to either be 1 or 0. Okay, it's either going to be my estimate from a single permutation, a single entry here is going to be either 1 or 0. But I'm going to make k of these estimates, and they're going to average out to be something useful. And if I increase k, the estimate will get better and better. Yeah.
K in this case was 6, right?
No, k is I've only done k equals 1 here so far. N was the size of the domain, which was 6 here. It turns out n is not going to matter. K, I've only done one example permutation here. I need to do k of these permutations, which might be, let's say, in your homework, I think you'll look at 160 permutations. Okay. Okay, you're going to get 160 different length vector here, which will be the representation. And as that number k gets bigger and bigger, it's going to get a better and better estimate. But if I just use 1, k equals 1, one estimate, it's either 0 or 1, which is pretty crude. Okay? But the main kind of highlight here, and I'll expound on this on the next slide, is that the expected value of Jacquard similarity between I and I prime is going to be exactly equal to the Jacquard similarity between AI and AI prime. Okay? So it's going to have exactly the right expected value. It's going to be a crude estimate, it's either 0 or 1, but the expected value is right. Yeah?
So are we doing the Jacquard similarity between the different vectors or sets? Sorry.
I'm only going to look at 2 of the sets so far. So think of which here is 2 of the columns. If I look at any 2 columns, and it doesn't matter which 2 columns I look at, and this is important, right? The Jacquard similarity is going to be I'm going to get the right expected value of the Jacquard similarity by checking if their top bit matches. Right? So columns 1 and 3, their top bit matches. Whereas columns 1 and 2, the top bit does not match. Well, if I look at it, actually, so I think the Jacquard similarity is actually larger between 1 and 3, but overall, as we'll see, you're more likely to get a match the larger the Jacquard similarity. The smaller the Jacquard similarity, the less likely you are to get a match here. And it turns out it's exactly the right expected value.
I guess the intuition behind why this works is that when you randomize the rows, like bits that are the same in each column will move together, right?
Yeah, right. So the rows move together, right? So the ones that match, they move together. And I'll go through the analysis. It's pretty short analysis. I don't do too many proofs in this course, but I'll go through this one because it's pretty short, just to see how it works. Yeah.
Why did you set the number of repetition for trial in step 3?
Oh, 2. I repeat steps 1 and 2, not 12 times. So steps, make this more clear. 1 and 2 for k times. Yeah, so k, let's say 160 is what you use for your assignment.
K is some sort of arbitrary value that we choose, is that right?
Yeah, I mean, it shouldn't be totally arbitrary, but it's either determined by, well, I only have so much patience or so much space, or I want to achieve a certain level of accuracy guarantee, and then I can figure out what k needs to be to get that accuracy guarantee. Yeah, so it's not totally arbitrary. The larger it is, the more accurate you are, and we can quantify that. And so then you can use that as a guide.
Is this kind of a relation to, like, if we just compare everything, it would just be very expensive, so we're just doing this randomly a certain amount of time?
Yeah, we're going to do this randomly, and this will be a representation, and we're not going to see in this lecture why looking at all pairs, or have a query web page and find the most, but that is a lot slower than I want to do. I'm not willing to spend that computational time in this case. Right, so we're adding modeling error, and we're adding, well, the modeling error we have to add just to compute the distance, but we're adding some extra error on top of that here in this representation, which in the next lecture, next week, we'll see how to quickly answer these questions. And then your third homework, you're going to do kind of a few experiments along these lines. Yeah.
I'm curious how this would be different than just picking a random row, as opposed to like permuting the whole thing. Like we just pick a k.
If you pick a random row and check, yeah. So in this case, you could probably work out an analysis to check that way, because the number of rows n here is not too big. It's 6, right? And most of them have 3 to 4 bits of them, anyways. But the problem is with things like text strings for kgrams. Like, what if I pick x, g, y? Right? That probably never shows up in any of the documents I have. So then I'm going to keep getting these things that doesn't show up anywhere. And so this has a clever thing that it allows us to ignore the rows which are all zeros. If I throw more rows which are all zeros in it, those are never the top one for any of the vectors, even if they show up top in the permutation. Right? So it has this advantage that will allow us to kind of do this quickly, independent of the size of the domain. It'll only depend effectively on the number of 1 bits. That's all we'll have to look at. Yeah.
So what exactly is I prime here? Is that like EI prime?
These are corresponding to 2 of the documents, or 2 of the sets that I'm starting with. Yeah, I used I to index the sets or the columns, and I'm just, instead of writing out the bit vector bi prime, it gets small in the numerator, I just wrote out the indexes. Okay. So this is kind of, it seems not too hard to do. This is the wrong way to implement it. We're going to do kind of an approximation of this technique, and that will be much easier to implement it. You won't need the intermediate representation or these bit vectors or anything like that. Before I show you that, I want to explain why this works. And I'm going to show you that the probability that m of I equals m of I prime, and so these are any 2 representations that I've done this permutation then top bit kind of approximation of. This is going to equal the expected value of the Jacquard similarity of I and I prime. This is the one that I'm kind of the probability they match is going to give me a 1 if they match and a 0 if they don't. Right? So this is the probability is equal to the expected value that I'm going to get of the M representation, the kind of approximate representation, which is exactly going to be the expected value of AI prime. Okay, so I'm going to prove this statement here to show you that I get the right expected value in this way of doing this approximation. Okay, and so in order to understand this, we're going to think of the rows. I'm going to have 3 types of rows. We're going to say Tx is going to be the x rows with a 1 in both columns. Okay, so this is a set of the rows that have 1 in both columns. This is where they both have this kind of item in the set. There are going to be a set of y rows with 1 in exactly 1 column. All right, so that means 1 in one column and 0 in the other. That means one of them has an element, but they don't match. They don't both have an element. And TZ is going to be the Z rows with a 0 in both I, BI prime, and let's say I have 1, 0, 0, 1, 1, 1, 0, 0, 0, 1. Okay, so then this is going to be a type Y. This is type Y. This is type Y. This is type X. This is type Z. And this is type Y. Okay? Right, because it has X, they have to 1 in both. To be 1 in exactly 1 row, that's Y, Y, or Y. And Z is 0 in both rows. Okay, and if this is my representation, then I can say that the Jacquard similarity between AI and AI prime is going to be exactly X over X plus Y. Right? It's the intersection, which is all the rows that have both 1s, over the union, which is they can have at least 1 X. So that's either type X or type Y. It does not involve type Z at all, right? So this is nice about this, it's no involvement about type Z, only depends on types X and Y, okay? And so then if I do and then if I think of them as rows, kind of these rows individually, the probability that M of I equals M of I prime is only true, equals 1 if and so only if the top row in the permutation is type X, ignoring type Z. Okay, so I can ignore the type Z rows. That's not going to be the top bit for either row. But if a type Y row is ahead of all the type X rows, then it'll trigger, it'll find the top 1 bit for one row, for one column, but not the other. I can only have a matching thing if the top row among the X and the Y rows is an X type. Right? And because it's a random permutation, the probability that that occurs is exactly X over X plus Y. Right? I can pick any of the X or Y rows to be the top out of that set. And if it's an X row, then I get a match. If it's a Y row, I'm not going to get a match. Okay, so and this is exactly the probability that they match. Right, so this is exactly the probability that M of I equals M of I prime. All right, so this is kind of a short and kind of sweet proof about why this works. And it's nice, it highlights that the 0 rows you can ignore, and kind of explains why this works. Okay, a couple of things to point out. This representation does not know anything about the data in choosing the permutation of the rows. This is important because it means that this holds for columns 1 and 2, but it also holds simultaneously for columns 1 and 3, or 2 and 3 and 4, which have no relation. It didn't know anything about the data to create this representation, yet it gives me the right expected value for any pair I check it. Right? So I can create this representation without knowing what my data looks like, and but I can still use it for anything in the future. So I can create the representation for a bunch of documents ahead of time, and then as I get more documents, I do the same trick later, the same exact permutations later, and I can still use that comparison. I don't need to know what the data looks like ahead of time. All right. Okay, so does this make sense? Okay, hopefully if you enjoy seeing why it works, you've seen why it works. If not, it's probably won't be I won't be on the test. But hopefully it was informative. Okay. Okay. Well, let's see. I quickly want to go through now the question: how big should K be? This is, remember, the number of the permutations, right? So how many permutations do I have to do? How many long do I have to make my vector representations to get in order to get a good estimate? Okay, I talked about doing one representation. One representation gave me either 0 or 1, which is a really crude estimate. But if they collide with the right probability, as I do more and more of them, this estimate should accumulate to something closer to the right expected value. So how many people have heard of the central limit theorem? How many have not heard of the central limit theorem before? Oh, Okay, so the central limit theorem basically says if I do a bunch of random things with the right expectation, then I'm going to get a lower and lower variance in my estimate as I average these events. And there are ways to specify it. If you take a stats class, you specify it one way. If you took the 3190 class, we saw other ways of specifying it. And so I'm going to just quickly do a review of one of those ways for you 3190 students, and we'll do a quick application of this to get a sense of how big K has to be. So there's this Chernoff-Hofting bound, which is kind of a very useful bound that says if I have, I'm going to have let's say I'm going to have R random variables, which are going to be, let's say in this case these are IID random variables, x1, x2, up to xr. And they're IID, so I'm going to say the expectation of xi is going to be equal to mu. Okay, they all have the same expectation. In this case, my random variables are going to be effectively these, each of the result of each of the permutations. Right? They all had the right expected value. Right? Every time I did one of these permutations to get one element of my vector representation, it's going to, or for a comparison, it's going to have the right expected value. Okay, and what I would like to do is to use the average. I'm going to set, let's use A, let's do M equals 1 over R, sum of I up to R of xi. Okay, so I know that the bilinearity of expectation, that the expected value of M is equal to the expected value of xi. Right, so if I take a bunch of these representations, I get a 0 or 1, and I average them, that's going to be my estimate of the Jacquard similarity. Okay, I'm still writing out this general theorem here, but kind of translating it, translating this on the fly. Okay, and so the Chernoff-Hofting bound, well, let's look at just the Chernoff bound here. Then I'm going to assume that each xi is going to be 0 or 1. Okay, each xi can take in a value 0 or 1, which is the case that we're in so right now. Okay, if the Hofting version is more general in what these can take on, then what's known is that the probability that the difference between M and the expected value of M, which is my average representation, right? The probability that the difference between these is greater than some error tolerance epsilon. Okay, this is my error tolerance, and let's say this is 0.05. Remember, the Jacquard similarity is between 0 and 1. Let's say I want to be off by at most 0.05. The probability that I exceed this error is going to be less than or equal to 2 times the e to the power minus 2 epsilon squared times r. Okay? So I want the probability to be small. I want the right-hand side to be small. Okay? And if I require a smaller error tolerance, so that this would be then I often call this delta, which is the probability of failure. And if you looked at the bonus question, it was asking about using a representation. Okay, a different sort of problem, but I want the probability of failure to be small, and this is e to this power which is a negative. That means as this quantity gets larger, it's going to go down. E to the negative 100 is going to be a very small number. E to the negative 0.001 is going to be close to 1. Okay, and I've got a 2 in front here. There are versions that you can sometimes get rid of this 2, and there are lots of versions of this bound, but this is an easy to work with version. Okay? And so as I increase the number of random variables, this quantity is going to get larger. The probability is going to go down. As I make my error tolerance smaller, then this quantity gets smaller as well. So if I require smaller error tolerance, I need more random variables to get there. Right? I need my k value to be larger. Right? So in this case, r is equal to k, the size of our vector representation. Okay? So let's go and plug in r is equal to k here. Okay? Okay, so let's say I want to get 5% error, and I want the probability of failure to be, let's say that this to be, let's say I set this to be equal to be 0.1. So 10%, only 10% of the time, I have more than 5% error. Yeah?
In your notes, you have negative 2 alpha squared over k instead of 10k.
Yeah, so there's some version, there are different versions of this, and in the notes I may have been taking a sum instead of the average. Is that right? If you take this, if I'm looking at how close is the sum, then this gets multiplied by k here, but then I also multiply epsilon by k, or then I divide.
Dividing epsilon.
Yeah, so I could be messing something up, but I think you're looking at a version where I'm taking the sum instead of the average. Yeah, so the version directly in my lecture notes uses a sum instead of an average, and that's why it's different. And then you get the k gets in a different spot, but if I divide m through by k, let's say I divided m through by k here, divide epsilon through by k, and then the k winds up in a different spot over here if you push it through the algebra. There are different versions of it. For the lecture, let's look at this one. If you look in the textbook, this is the one that's written in the textbook. Except there's this big delta term, which I've set to 1. Okay. Right, and if you'll see, the k's will cancel out in the lecture notes. There's a k squared over k that shows up, and so you end up getting the k in the numerator anyways. Okay, good. So if we set this, so if I say I want this to be equals to 0, 1 here, then I can just do some algebra on here, right? I can say 0.1 equals to 2 times e to the negative 2, and this is 0.05 squared times k. And so I can do, let's say I do a natural log of 0.05, that's 0.01 divided by 2, is equal to negative 2, and this is 1 over 400 times k, right? And so then if I solve for this, it's going to be k is going to be equal to, I'm going to push the negative inside the log. What that does is it makes it a log of 1 over 0.05, because this value is actually negative already. Okay, so I'm going to get, let's see, I'm going to get 200 times natural log of 1 over 0.05. Okay, this is how large k needs to be in order to get this. And this turns out to be log of set in my notes. Oh, I use different values in my notes, but let's say this is log of 20, right? Natural log of 20 is going to be about, what is about 4 or 5? So let's say 5. Oh, 3? 3? Okay, so it's about 3. So this equals about 600. Okay, so this says Okay, this says in order to guarantee that with at most 10% probability, I get at most 5% error, I need k to be 600, which seems kind of large. My usual back of the envelope for these things is roughly 1,000 is a good number to get a reasonable error. You know, I'm going to argue you probably don't need it even to be 600. I think around 100 or 200 is probably going to start being actually useful. Okay, part of the reason for this is that if it fails, it usually does not fail in a way that's totally catastrophic. If it fails, it's usually, well, not too much bigger than epsilon, not too much bigger than 0.05. Okay, and that's only 10% of the time. 9% of the time, it did pretty well. And we'll see the gaps we're going to need to separate things, you'll see in your homework, are usually, in a lot of cases, are going to be, might be even larger than this, as you're going to get some gap which is meaningful. Two things which are very similar might have 0.9 Jacquard similarity. Two things which are different enough might have something like 0.7. Okay, so for using this as a quick check, so that was a gap of 0.2, and we only had an error of 0.05. Okay, so you can change this there as well. But if you want to use this for like doing a web search engine over Wikipedia, which you could try and build, you'd probably want this to be at least 1,000. But at that scale, 1,000 is probably going to be useful. Okay, we're going to see there's also, keep in mind, there's modeling error, how you chose the k-grams, and there's going to be other errors in this process. So don't trust these numbers totally. These sort of numbers for this, with this amount of modeling in it, probably are fairly reasonable. Okay, so this is just kind of you can actually quantify this error. I don't think we're going to quantify any more errors like this in this semester. Maybe one more time, but yeah, probably one more time in the semester. But just give you a sense of this. We're going to, and a lot of things we're going to do, we're going to take a lot of small measurements, and as they add up together, they're going to give us a good estimate of something more complex. And this is one example of it. Okay. Okay, so right now I've told you something where you I've taken something that a set from a domain of size 6, I've told you to blow it up to size 600, and it has all this extra space you have to deal with, and the way it's getting further from useful. I'm going to start to bring that back now, and then next lecture we're going to actually show another algorithm that sits on top of this, which allows us to do kind of filtering of things which are quick very efficiently. But first I want to show how to do these fast min hash, so signatures. Okay, and so these signatures, by this I mean these vector representations. I want to create this k-dimensional vector representation with these k-independent things. And the trick is to have some sort of hash functions. Okay, so I'm going to go from a set AI to vector vi in and this will be in the integers. It's going to be k-dimensional. Okay. Okay, and the way I'm going to do this is I'm going to have k hash functions, okay, which are going to go, each hash function, hj, is going to go from the, I'll write this, from some domain. Let's, it can be a representation of the text, but let's say it's of the domain of size n to another domain. Let's say this is of size n prime. Okay, so I'll discuss how big n prime needs to be. It can be, when we talked about these hash functions, it's this m quantity, how big we want that to be. Maybe it's the same size as n, maybe it's smaller. It's not going to matter too much. Okay. Okay, and so then I'm going to have an algorithm. The algorithm. So I'm going to basically for all the elements in each set, I'm going to do the following. For each j in my set, and each of these hj's are going to be drawn randomly from a hash family. So there's now randomness. These are basically, of course, each hash function I think of being the permutation I'm doing. But I'm going to do something else to approximate the permutation. Okay, so for each hash function, let's say from j equals 1 to k, I'm going to say if the jth hash function on I is less than my vector representation vj, the jth element of my vector, right? So this will be, let's say this we have I is straight. I should have overloaded I here. Let's call this each element x. We'll say this is AI. Say this is x. And so I'll say vi, the jth element of this vector. Okay? So if it's less than the jth element of the vector, then I do a replacement. Okay, and so here's the whole algorithm. Once I've created these hash functions, so I'm probably init that the v of I of j equals infinity, for all j in 1 to k. Okay, but here's the whole algorithm. Okay, so I'm just going through all the elements of the set, just one by one. And then for each of the hash functions, so I only have to read the element once while it's in memory effectively. For all the hash functions, I compare it against the current value. And if it's less than that, I just update that value. The hash function is effectively acting like a random permutation. Okay, it's a deterministic process. The hash function might have collisions, right? It might have collisions, but it's only a problem if there's somehow a collision at the smallest value I see, which is probably pretty rare. Right? If I make n prime large enough, then the probability of having a collision is like, what if I make m prime to be n cubed, right? Then the probability of having a collision is going to be very small. And it doesn't matter. I'm not storing an n prime length array anywhere. So I can make n prime to be m cubed, and then the probability of collision is pretty small. I probably don't need to make it that big, because I only care if I have a collision at the very smallest value, the smallest thing I generate. And this effectively gives me a random permutation. And so I don't need to actually store the vectors and do the permutation. The hash function does this for me. Okay, and I do it with one pass over the actual data set, the actual set. Okay, so this is one pass over the data. So that means if I have something already set up in my set AI, well, then I can just read it once. But I don't actually need to create that set. I can actually, if I'm k-gramming a document, I'm reading through the document and creating these k-grams. And as soon as I have a k-gram, I don't need to store it. I just throw it into all my hash functions and check if the value is smaller. So I can create these vector representations as I'm reading over my document. So I just need to scan my document once, and I can output these hash vectors and update them. And as I keep reading, they keep updating, and they get smaller and smaller values. Right? So I can do this in one pass once I've set up these hash functions. And the hash functions are fixed, and they're stored. So if I have another document I need to read, I need to use the same hash functions. Those are effectively storing the same permutation of the data. But I don't even, but I don't need to know how big is n, right? I don't really, I don't need to I don't need to know this value. I can instead say, instead it's, say if I do charactergrams of length 3, and I have an alphabet, this is an alphabet of the characters, and then I have a 3 gram of those characters, well then this can be then I can use this domain instead. My hash function can go from character strings of length 3 to n prime. Right? I don't even need to know what the real set of possible things are. I just need to be able to define it on charactergrams. Or if it's wordgrams and I'm using something that can take in a string of like any reasonable length, then I can just plug in strings into here. Right? So I don't even need to know the size of these sets. It makes them much more general. And I just make one pass over the data as I'm doing this, and I get these vector representations. And if they're large enough, they approximate the Jacquard with at least the right expectation. And if k is large enough, then it's going to be a better and better estimate of the actual Jacquard similarity. Okay, so this is what I wanted. Let me write up one more important thing just to make clear. We're going to do like a Jacquard estimate, let's say of size k, between, say, vector vi and vi prime. And this is explicitly going to be 1 over k sum of j equals 1 up to k of, and we'll write this as 1 if m of I equals mj of, let's write this as v of j of I, how did I change my notation? Okay, we'll do v of I of j is equal to v of I prime of j, 0 otherwise. Okay, so that's how you get your Jacquard approximation here by kind of averaging these 1 bits. Okay, so it's not exactly the Euclidean distance we're using here. It turns out for what we'll do next, locality-centered hashing, this will actually be easier to work with than Euclidean distance in this setting. So so we kind of see how to quickly get this cleaner representation. We still can't answer these big scale like similarity questions. Next week, Wednesday, we will see how to use locality-sensitive hashing with all these 1, 0 vectors, or these vectors if they match, in order to quickly find all the things which are similar. Okay.